I'll start with the most famous one, which is time-correlated single photon counting, or TCSPC. The idea of TCSPC is shown in this schematic at the bottom, and it's quite a simple idea. You have a pulsed laser, typically with a high repetition rate in the megahertz range. And when this laser fires, it sends an electronic trigger pulse that starts the clock of the counting electronics. The laser excites the sample, and the sample emits a photon of photoluminescence, which is detected using a PMT detector, which converts that to an electrical pulse, and this electrical pulse stops the clock. And the basic idea of TCSPC is that you want to measure the time between the excitation pulse and the detection of this photon. And then you record that time on a histogram that's stored in the memory of the spectrometer. And one of the key principles of TCSPC is that only a single photon can be detected for each flash of the laser. So you then repeat this process by firing the laser again, and you record a different time and plot it in the histogram, and then repeat this process millions of times to build up the complete photoluminescence decay of your sample, photon by photon. TCSPC is the method of choice for measuring fast photoluminescence lifetimes, typically on a nanoseconds to picosecond time range, due to its very high time resolution. The timing electronics of the FLS1000 has a resolution down to 305 femtoseconds. An example of TCSPC in use is shown here. So this was a decay of an organic molecule, 9-aminoacridine, which shows a nice mono-exponential fluorescence decay with a lifetime of 16 nanoseconds. The TCSPC technique can also be used to measure photoluminescence decays from semiconductor samples, such as perovskites. So here you can see that the photoluminescence decay of the perovskite has a very non-exponential behavior, and it was fit with a stretched exponential model, which returned an average lifetime of 36 nanoseconds. And TCSPC is ideal for characterizing both of these materials. As I said, TCSPC has a very high time resolution, and that allows it to measure lifetimes down to 5 picoseconds in the FLS1000. An example of this is shown here, which is the measurement of an organic molecule known as 4-DASP, which is a very short fluorescence lifetime. On the left is 4-DASP when dissolved in ethanol, which was found to have a lifetime of about 57 picoseconds. But when 4-DASP is dissolved in water, its lifetime shortens and was found to have a lifetime of 11 picoseconds. So this demonstrates the ability of TCSPC mode to measure extremely short fluorescence lifetimes down to 5 picoseconds. So TCSPC is the technique of choice for measuring short fluorescence lifetimes. The downside of the technique is that it becomes inefficient and slow for measuring longer lifetimes. And the main reason for this is because of this requirement that only a single photon can be detected per excitation period, so per flash of the laser. And TCSPC therefore relies upon high frequency, so high repetition rate lasers for fast measurements. So when you have short lifetimes, you can set your laser to a very fast repetition rate in the megahertz range, and you can therefore measure many photons very rapidly, and the technique is efficient. But when you're measuring materials with much longer lifetimes, you've got to reduce the repetition rate of the laser, and the technique becomes very slow because most of the time the spectrometer spends measuring no photons at all. It's waiting on photons to arrive.